So we've got this time the summation form, the sum from n equals 0 to infinity for 2 to the n x to the n. So we want to find a power series for the derivative of this function. And so we're going to say that f of x is 2 to the n x to the n. So first off, just to remind ourselves how these power series work, how else could we rewrite this series? This could be written as the sum from n equals 0 to infinity of what? Since they're both being raised to the power of n, we could make this 2x to the n if we wanted to. And we'd see that the common ratio each time is going to be what? Yeah, should be 2x every time, which would allow us to find the interval of convergence if we wanted to. It doesn't talk about that, but we will in a minute anyway. But if the common ratio is 2x, that means that f of x is what function? Should be 1 over 1 minus 2x. Right? And that's just from the form that we originally had, right? Everybody good with that? So what is the derivative of 1 over 1 minus 2x? So what is f prime of x? You can just use the reciprocal, right? The denominator is going to be 1 minus 2x squared. And the numerator should be the opposite of the derivative of the denominator. So that should just be a 2. 2 over 1 minus 2x squared. And so we should be able to write this as a nice simple power series by just doing a term-by-term differentiation of 2x to the n, or 2 to the n, x to the n. And so if we were to do that, 2 to the n is just what? It's just a constant. Thank you, Nick. So the 2 to the n is just a constant out in front. So all we really have to do is differentiate the x to the n. So we're looking at 2 to the n times, and well, what's the derivative of x to the n? It's n x to the n minus 1. Good or no? And we should be able to simplify this out a little bit. We should be able, oh, sorry, we should change the index. I forgot to do that, that's my fault. Anytime you take the derivative, you gotta change the index, n equals 1. And we should be able to rewrite this a little bit more simply, because it'd be nice to have everything that is my common ratio being to a power of n minus 1. So how could I turn 2 to the n into something that's 2 to the n minus 1? I just make it 2 to the n minus 1, right? And then I have an n, and then I have an x to the n minus 1. But if I made 2 to the n into 2 to the n minus 1, what do I have left over? I still have to put in an extra 2, which should turn this into the sum from n equals 1 to infinity of 2n times 2x to the n minus 1. Good or no? How I went from here to here, Molly? Or for how I went from here to here, or both of those? Yeah, so we were at 2 to the n x to the n minus 1. And it'd be nice, we normally want to have our common ratio, which we know is going to be 2x. We want that to each time have that same power, since we're multiplying by the 2x each time. And so if I turn 2 to the n into 2 to the n minus 1 times 2, right? 2 to the first and 2 to the n minus 1 is just 2 to the n. That's the same thing. I can then put the 2 to to the n minus 1 and the x to the n minus 1 together as 2x to the n minus 1, and then just multiply by 2n. This is normally the form we'd try to write it in. And what was our common ratio? Like we said before, our common ratio up here was r equals 2x. So if the absolute value of 2x has to be less than 1, that tells us that x is less than a half greater than negative 1/2, which tells us that the interval of convergence for the derivative is also negative 1/2 to positive 1/2. And we could, if we wanted to, go in here and look in Desmos at this. So our function was what? 2 over, I believe it was 1 minus 2x squared, right? And our summation was the sum from n equals 1. We'll just put like 50 up here. And we had 2n. And then we had 2x to the n minus 1. And so this should have been valid for negative 1/2 to 1/2. And up, there we go. That doesn't look right. But that's probably just because it's very slowly populating here. There we go. Now it looks better. So from about negative 1/2 here to positive 1/2, where we have this asymptote, lines up real nicely with here. And it gives us all these little points in here in Desmos because it's actually intersecting through the function all those tons of times that it's showing there, because this thing is really just a 50th degree polynomial here. Right, and so it's got lots and lots of little, if we were to zoom in on this, might have to zoom in a little further than Desmos can handle, though. You would be able to see tiny little oscillations in here at all those little places where it crosses through. Good or no? Any questions, any issues with these derivatives, taking the derivatives of a power series to get a new power series for the derivative of the function? Will always converge on the same interval as the original power series did. And you can just term by term differentiate if you need to. And if we wanted to, we could plug in n equals 1 to each of these, and 2, and n equals 3, and n equals 4, and actually come up with all the terms of the series, but that's sort of unnecessary. All right, let's look at another one. This one's going to be a little bit different. So we're going to look at 1 over 1 plus x this time. 1 over 1 plus x, which should be 1 over 1 minus negative x, right? Which means it should be negative x to the n. Or negative 1 to the n x to the n, right? Which is going to cause us to flip these signs every time. 1 minus x plus x squared minus x cubed, and so on. And we know, again, that this one is got an interval of convergence of negative 1 to 1. So we want to use this series to see if we can write out a series for the natural log of 1 plus x. Any thoughts on that? Yes, exactly, Aiden. That's what we're going to do. We're going to try to integrate this. And we're going to do a term-by-term integration of each term. And so if we were to do that, we know that the integral of 1 over 1 plus x should be natural log of 1 plus x, right? That's just, that's just our standard integral. So what we're going to say is, and we either have to write these as, and we can make the choice to write these integrals as an indefinite integral and solve for the constant, or we can choose to do them as a definite integral if we see a nice value that works out really well. So is there a value that I can plug into this function, natural log of 1 plus x, that will make it 0? If there's something we can plug in that'll make it 0, we usually want to try to do a definite integral. And so, yeah, if we plug in 0, right, this would be natural log of 1, which would be 0. So what we're going to do then is we're going to say the integral, and we're going to use the fundamental theorem of calculus here, the integral from 0 to x of 1 over 1 plus t dt should be the natural log of 1 plus x, right? Because I'll integrate this and evaluate it at x and integrate it and evaluate it at 0. And when we evaluate it at 0, that's going to give us 0, right? So we could, if we wanted to, the natural log of 1 plus x minus natural log of 1 plus 0, or just natural log of 1 plus x. Good? Okay, and we're going to note that I did not throw absolute value around these. And the reason why is, what's the interval of convergence for this? It's -1 to 1. So we're really only concerned about what's happening between -1 and 1, and between -1 and 1, non-inclusive of -1 and 1. The values inside of there are always positive, so the absolute value is redundant. Everybody good there? Conceptually with what we're doing, sort of to start. So all we have to do then is integrate our summation from n equals 0 to infinity of our negative x to the n, which is -1 to the n, x to the n. And how do we integrate -1 to the n, x to the n? -1 to the n is just a constant, right? And x to the n should just integrate to become x to the n plus 1 over n plus 1. Good or no? And we will say that this is valid for, and I'm going to make a little caveat here, at least for -1 to 1. And that -1 to 1 is the same interval of convergence that we had for the original one. And I'm noting that it is good for at least this because it might also be valid at the endpoints. And so we're going to think about these endpoints in just a second. Well, we're going to do them right now. But first, I'll answer Aiden's question. No, you don't need to move the index on this one, because that's what solving for the constant does. So like we went through here and we, so either doing the definite integral to plug in a value that we know eliminates the need to move the index, or finding a constant will eliminate the need for moving the index. But with the derivative, we're effectively like knocking off some terms, so we have to move the index up 1, but integration doesn't require you to move the index down 1. So you shouldn't ever need to do that. Okay, so first off, we've now got this new series, the sum from n equals 0 to infinity of -1 to the n x to the n plus 1 over n plus 1. Now, the question is, does this thing converge at either of the endpoints? So when we say it's at least, that means we need to check the endpoints. And checking the endpoints is something that we are going to spend a lot of time doing as we continue through this unit. And we're going to have some really good methods to prove whether this, whether this and other functions happen to converge at their endpoints, at the endpoints of their interval of convergence. But for now, since we don't have all these tricks at our disposal, we're just going to try and plug some numbers in and see what happens. So when we say check at the endpoints, what are these values? These -1 to 1 values are representing what? They are the values of what variable? Right, they're the values of x, right? They're the values of x for which this series is a representation of this function. So if we were to plug in -1 to our function, right? And I'm going to do this on the next page, right? We're going to talk about this is going to be about our endpoints here. Natural log of -1, and we're talking about the endpoint -1 over here. Natural log of -1 plus 1, does that exist? No. So this doesn't exist. Therefore, when we think about the endpoint of -1, we don't need to even worry about it. There's no point on our function at -1. So let's then think about the function at the endpoint of 1. Well, the natural log of 1 plus 1, that's the natural log of 2, right? So the question is, does the sum from n equals 0 to infinity of -1 to the n, and then instead of x to the n plus 1, we're going to replace the x with a 1 to the n plus 1 over n plus 1. Does this equal natural log of 2? And so that's what we want to know. That's what we're going to try and evaluate. Does that make sense to everybody? So what we've done is we've replaced the x with our endpoint. Everybody good with that? Conceptually, with how we're doing this, how we're checking for the endpoint? Or no? Right, we've taken our series and we've just replaced the x with 1. Everybody's good there or no?
Yes.
Okay, just making sure. All right, so there's 2 different ways we could do this. And for now, well, I mean, we're just going to do this using Desmos. All right, so yeah, Nick, the reason we need to check the endpoints is because unlike with the differentiation, we do the differentiation, it's always valid on exactly the same interval as the original function. But when we do the integration, there is a chance that the new series that we get for the new function that we wanted might also converge at the endpoints, not just at the basic interval of convergence that we started with. That's the only reason, is that that's just something about integration, is that when we do the integration, it sometimes allows us to converge at those endpoints as well. And so we were going to do this on Desmos, because Desmos will very conveniently, and we don't need the graphing part of it. It'll tell us what natural log of 2 is, it's that. And then we can put in our sum, right, from n equals 0, right? To, let's just start with 1, just so we can see the progression of it. And our series that we're now looking at is -1 to the n, 1 to the n plus 1, which we really don't need to write in because 1 to the n plus 1 is always just going to be 1, but we'll put it in there, over n plus 1. And so if we go from 0 to 1, we're at half. If we go to 2, 3, oh no, I messed that up. Okay, 3, 4, 5. We can see it's oscillating back and forth. At least currently, it looks like it's oscillating back and forth around the natural log of 2. Right, 0.63, 0.74, 0.64, 0.73, 0.65, 0.73, 0.658, 0.725, and so on, right? It looks like it does maybe get closer and closer to that value. Let's try 30. If I plug in 30, we're at 0.709. If I plug in 40, getting closer. 50, getting closer. I meant to do 100, but 110 will work. 1,000. Looks like it's getting closer and closer and closer and closer and closer to that value of the natural log of 2, doesn't it? Do you guys agree with that? $100 million seems to be a difficult calculation for it. There it goes. So that by the time we put in 100 million there, we are, you know, whatever that is, a 10 millionth or so off, 5/10 millionths or so off from the original value. So I would argue that that looks like it's converging. True? Do you guys agree that that looks like it's converging to natural log of 2?
Yes.
1. So what we would then say is we could say that, and we don't have, like I said, we don't have proof of this, we just have some sort of empirical evidence here. It's not really evidence, it's just an empirical observation. Maybe that we have an interval of convergence that is actually -1 to 1 inclusive of the 1. And it does. This series does converge to natural log of 2. But yeah, I guarantee you it does. And we'll prove why later on this year. Everybody good with that? All right, so here is the idea behind the term-by-term integration. This is just sort of the written out thing that I had before for the derivatives, right? If we have each of the terms, we can just integrate each of those terms and write out the series, right? And remember that any constant out in front of here is just that. It's just a constant out in front of it. It stays there when you do the integration, okay? And so we know that if the series converges for all of the x on this interval, then so does the integral of that series. And as I just said, you also need to check the endpoints. And you also need to check the endpoints because it could potentially converge, as we just saw, at those endpoints. Good or no? All right. Let's see if we can.
Mr. Bachelor.
Yeah.
I typed a question in the chat for the last slide.
Oh, I must have not seen it. I did not see it. Okay, here we go. But there will be a case where instead of stopping at 1 over there, nah, so it will include only the original amount and potentially the endpoints, but it will not go beyond that interval. Other than maybe at the endpoint. Yeah. We are going to see some series that though do have an interval of convergence. It's more than like this -1 to 1, or for potentially for all real numbers as well. But then the integral of them would also have that same convergence. So, yeah, cool. So let's see if we can now find a power series for inverse tangent of x. Any thoughts on how we might do this? Any thoughts on this? The inverse tangent of x. Okay, yeah, so you hopefully noted, Elon, that the derivative, right? This is what I'm sure this is where this came from. The derivative of inverse tangent of x is 1 over 1 plus x squared, which is the same as 1 over 1 minus negative x squared. And we could use the power series for 1 over 1 minus negative x squared, which would be the sum from n equals 0 to infinity of negative x squared to the n. Okay. I assume that's where you're going with that. So how could we rewrite negative x squared to the n? We should be able to rewrite this as n equals 0 to infinity of what? Negative 1 to the n, and then x to the 2n, right? X squared to the n, just multiply the exponents, you get x to the 2n. Good or no? Hopefully everyone's good. So that should tell us then no, it's not negative 1 to the 2n because the negative 1 is not being squared. It's negative 1 x squareds to the n. So it's negative 1 to the n, x squared to the n. Okay. All right, so we should be able to then say that the inverse tangent of x equals the integral of our series, and we're going to write it as negative 1 to the n t to the 2n dt. From where to x? Is there a good value that when we plug it into inverse tangent, we'll get 0? Inverse tangent of 0 is 0, isn't it? Right? So let's do this. The inverse tangent of x is equal to the integral from 0 to x of negative 1 to the n t to the 2n times dt. And what does that integral look like? It looks like the sum from n equals 0. Oh, I should have forgot my n equals 0 to infinity there. N equals 0 to infinity of negative 1 to the n. And then our x to the 2n becomes, or t to the 2n becomes an x to the 2n plus 1. And we'll divide by 2n plus 1. Good or no? This is our series for inverse tangent of x. And let's, before we worry about the interval of convergence, well, actually, let's do that now. So what was our original? Our original one came from negative x squared. So we need absolute value of negative x squared to be less than 1. Well, the absolute value of negative x squared is just x squared. We need x squared to be less than 1. So if x squared is less than 1, that's going to tell us that this converges from negative 1 to 1. Right? And so we're going to say at least negative 1 to 1. And we're going to, first off, just check and make sure our series looks correct in Desmos. And then we're going to try to evaluate this at the endpoints. Sound good? Everybody good? Makes sense? Everybody's on the same page here? So here's arctangent of x. And our sum, which is the sum from n equals 0 to, let's just put in like 50 there. We've got negative 1 to the n, and we've got x to the 2n plus 1, all of that divided by 2n plus 1. And we'll give it a second there to figure out what it's doing. There it goes. And so we can see it sure looked like it converged there for at least negative 1 to 1, right? Everybody good there? All right. So how about the endpoints then? So at x equals negative 1. What's the inverse tangent of negative 1? No. Whenever you take an inverse tangent, you always get at a value between negative pi over 2 and pi over 2. Negative pi over 4. Okay. So that means that if I take negative 1 and plug it into my series for x, the hope is I'll get negative pi over 4. So negative 1 to the n, and then negative 1, since we're plugging in negative 1 for x, to the 2n plus 1 over 2n plus 1. And so the question is, does this sum equal negative pi over 4? And I could rewrite negative 1 to the n and negative 1 to the 2n plus 1 as negative 1 to the 2n plus 2 if I wanted to. But I'm not going to bother to, because I'm just going to go over here in Desmos and just replace this x with a negative 1. And so when I do that, and I look at the first 50 terms, negative 0.790299653247 looks pretty good, pretty close to what negative pi over 4 is. If I throw in, 500 terms there, it's getting even closer. And if I put in 500,000 terms, it's looking awfully good, right? It's off by a bit still, but it's getting pretty good. Would you all agree?
Yes.
Yeah. So we would say that that certainly seems to be converging, and it does. And what if we changed it to a positive 1 there, and this to a positive? Well, looks like we're still pretty darn close, right? So it would appear that this is true. And since I'll write this out, the inverse tangent of 1 is pi over 4. And we just found that the sum from n equals 0 to infinity of negative 1 to the n, 1 to the 2n plus 1 over 2n plus 1 equals pi over 4. We said yes. So our interval of convergence should be, for this one, negative 1 to 1. And like I was saying, we don't have a way to prove that yet. It just sure looks like it is. Empirically, we can say that we think it is, but that doesn't mean that it for sure is. We will find ways to prove that it is eventually this year. Any questions on that? All right. Let's do one like this. And we're going to, instead of doing a definite integral this time, we are going to do it as an indefinite integral. So we want to find a power series representation for the natural log of 3 minus x. And so what function, when we integrate it, gives us the natural log of 3 minus x? That shouldn't be that difficult of a question. If we integrate the opposite of 1 over 3 minus x, that's just this integral, isn't it? Isn't that natural log of 3 minus x? And so we should be able to then say that, what is the, I think somebody put it in here, Elon put it in there, right? It's not an x minus. Yeah. Can you guys hear me now? I don't know what happened. My laptop was doing something there. I don't know what my laptop was just doing. Hold on. Okay, so we're trying to find a power series representation for natural log of 3 minus x, right? We said that the integral of negative 1 over 3 minus x should be the same as natural log of 3 minus x. Everybody agree with that statement?
Yes.
Okay, so a cool little thing that we can do if we want to find the power series representation for the 1 over 3 minus x, because we can throw that negative sign out of there and not even have to worry about it. Okay, if we're looking for the representation of 1 over 3 minus x, we can, and you probably will see in the notes for a lot of the power series stuff, I just kind of factor this 3 out of here to make it, this is 1 over 3 minus x should be equal to 1/3 of 1 over 1 minus 1/3 x. Everybody good with that? Right, if I distribute that 1/3 through there, that's still going to give me 1 over 3 minus x. So this should allow us to get a nice, simple, easy power series representation for 1 over 3 minus x that doesn't involve like an x minus 2 or something in it. So how would we do that then? We just have to let our power series for 1 over 3 minus x equal what? Should be 1/3, because we have to keep the 1/3, and then it should be times 1/3 to the n from n equals 0 to infinity. Would you all agree with that?
Yes.
Okay, good. And so how could we or sorry, not 1/3 x, 1/3, but 1/3 x. How could we rewrite this so that perhaps I could get everything within, either everything to some sort of power, I guess is what I'm looking for. Why is the first part not 1/3? Okay, well, so yeah, I was just dealing with 1 over 3 minus x, but if we want to put the negative out in front, put the negative out in front, put the negative out in front. Is that better for those of you that wanted the negative? What do you mean, why is the first part not 1/3? 1/3 to the n, Nick? Yeah, so the first part's not 1/3 to the n because all I did was I was turning 1 over 3 minus x into 1/3 of 1 over 1 minus 1/3 x. And so the thing that gets raised to the power of n is only what we've replaced x with in our original 1 over 1 minus x power series. Does that make sense? Or no?
Yes.
All right. Okay, so now what we've got here then is we've got the opposite of the sum from n equals 0 to infinity of, I've got an x to the n in my numerator, right? But what do I have in my denominator? I've got a 3 times a 3 to the n. Well, 3 times 3 to the n should be 3 to the n plus 1. And so we could write this, just the series for the opposite of 1 over 3 minus x as the opposite of the sum from x to the n over 3 to the n plus 1. And the r value that we were looking at here was 1/3 of x, and that would have to be less than 1. The absolute value of it would have to be less than 1, which would give us an interval of convergence for this to be -3 to 3. Everybody good with that, or no?
Yes.
Okay, so, and I don't know, sounds like we're good now. So we then should be able to say that the natural log of 3 minus x, which is the integral of this, should be the integral of this function that we had way down here. All right, so I'm going to give us a new page for this and just say that we're now looking at the opposite of the integral of the sum from n equals 0 to infinity of x to the n over 3 to the n plus 1 dx. And so now when we integrate this, and since I said we're going to do one as an indefinite integral, we should end up with the opposite of the sum from n equals 0 to infinity of x to the n plus 1 over n plus 1. That's how we'll integrate that, right? Raise it up to the power of n plus 1, divide by n plus 1, and 3 to the n plus 1 still. And then we're going to have to add some constant to that. Yeah. And we can find out what that constant is by choosing some value for x that we can easily evaluate this series at. And there's only really one good value for x that we could evaluate this series at. And what would that be? That'll make it really, really easy to evaluate. Well, no, to evaluate this series itself, right? Because we don't know what this constant is. We need something that we can evaluate this at. We can say the natural log of 3 minus x is equal to this. So we need to find a value that we can, of x, that we can evaluate that we know this thing's value at. But if we plug in 2 to this, 2 to the n plus 1 over n plus 1 times 3 to the n plus 1, we may not know the value of that so easily. So what's a value of x that I could plug in here that makes it really easy to evaluate? Even 1 is still a little bit difficult. 0, yeah, 0 is a good choice. If x equals 0, then we end up with the natural log of 3 equals, well, all of this just becomes 0 to the n plus 1 over some number times some other number plus our constant, which tells us that the natural log of 3 equals 0, because 0 to the n plus 1 is always 0, and 0 over a bunch of stuff is just 0. And the sum of a bunch of zeros is just 0, and the opposite of 0 is just 0. So we end up with 0 plus our constant, or a constant of natural log of 3. And so we could then say that a power series representation of this that now includes some constant in it is the natural log of 3 minus, I'll just put it out in front, the sum from n equals 0 to infinity of x to the n plus 1 over n plus 1 times 3 to the n plus 1. And this should have, and we're not going to bother checking the endpoints here, but it should have at least a convergence of -3 to 3, which was the same as our other. Good or no? Okay, and just a side note, having that constant out there in front is fine. There's nothing wrong with that. And there's no good way to get rid of it. So if you want to get rid of it, sorry, tough luck, you can't. There's no good way to get rid of it. All right, one last thing for today, and then we'll be done with all of the basics, the real basic stuff with power series, and we're going to move into some more complicated power series, or more complicated series stuff. So let's say we've got this function here. This function defined by this power series, 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial and so on. It's the sum from n equals 0 to infinity of x to the n over n factorial. We're all familiar with what factorial is, right? What the exclamation point means. Or no, for my nose, factorial, somewhat. Yeah, factorial just means like if I said let's give us a new page here. If I said, 3 factorial, that just means 3 times 2 times 1. If I said 100 factorial, that means 100 times 99 times 98 times 2 times 1. Right? And just take all the numbers and multiply it down, multiplying every single number in between. Yeah. Everybody good with that? That's factorial. Seen that before sometime in your life, maybe. 3 factorial is 6, right? 4 factorial is 24. 5 factorial is 120. Just multiply 5 times 4 times 3 times 2 times 1, you got 5 factorial. Okay, all right, that's factorial, important. So here is our series. It is x to the n over n factorial. And I want you to figure out what this function represents without, without using a calculator, without going into Desmos and just graphing it. I want you to tell me what this function represents. In fact, let's do something with this. What is f prime of x? What's the derivative of 1?
Zero.
All right, what's the derivative of x?
1.
1. What's the derivative of x squared over 2 factorial? I mean, x squared over 2 factorial is just x squared over 2, right? So what's the derivative of 1/2 x squared?
X.
Should just be x, right? What about x cubed over 3 factorial? Well, that will become 3x squared over 3 factorial. And what happens to the 3's? They should cancel out, right? So it's x squared instead of 3 factorial. If I have a 3 in the numerator, I could just make that a 2 factorial. And what about x to the 4th? Well, that becomes 4x cubed, right? The 4, we'll get rid of the 4 from the 4 factorial and drop it down to a 3 factorial. So that'll become x cubed over 3 factorial. What if I take the derivative of x to the n over n factorial? That should become x to the n minus 1, right? Over, well, the n will cancel with that n, over n minus 1 factorial. What would the next term be? Should be just x to the n over n factorial. What do we notice? You should notice something very cool and interesting. What do you notice? Yeah, it's the same, but it's shifted over slightly, right? So, I mean, sort of slightly shifted over. We've got a 0, right? And then a 1, and then an x, and x squared. So we have an extra term in here, 0. Well, so I could then say that f prime of x, because when we do these, it always shifts down, right? N equals 1 to infinity of x to the n minus 1 over n minus 1 factorial, right? Well, if I think about that, what do I get here when I plug in 1? I get x to the 0, which is 1 over 1 minus 1, which is 0 factorial. Something of note here is 0 factorial is defined as 1. That's an important fact that you're going to need to know for the rest of your life. 0 factorial is defined as 1. So if I have that, I have x to the 0, 1 over 1 factorial. Well, the first term is actually just the 1, right? The 0, we don't worry about. And so it's really the exact same series. This could be rewritten if I wanted to as the sum from n equals 0 to infinity of x to the n over n factorial. Well, what if I were to try and do the other thing? Instead of derivative, what if I were to take an integral of this? Right? The integral of f of x dx should be, what's the integral of 1? Should be x, right? Plus the integral of x is x squared over 2. 2 is the same as 2 factorial, right? Yeah. And then what about the x squared over 2 factorial? Well, that should become x cubed over 2 factorial times 3, which would be 3 factorial. And the next one, x cubed, would become x to the 4th over 4 factorial, right? And so on, wouldn't it? The x to the n minus 1 term would become x to the n over n factorial. The x to the n term would become x to the n plus 1 over n plus 1 factorial, and so on. And what do you mean, why is it the integral of f of x? Isn't this the integral of f of x? The integral of this, integral of 1 is x. Integral of x is x squared over 2 factorial. X squared over 2 factorial becomes x cubed over 2 factorial times 3. I'm not sure what your question is, Nick. I mean, we were just taking the integral to see what happened to it. Just for fun, you know? Yeah. And what do we have at the end of this? We have some constant, right? True? Got some constant there. Well, if we put in, I don't know, let's say what's an easy value to integrate this at instead of doing it with the constant? Would 0 be an easy value to evaluate this at? And let's, instead of having this in here as an x, let's change that to a t now. Kind of how we did those first ones. Right, the x gives us this, and then at the end, what do we need to subtract? We would need to subtract minus f of 0. And what's f of 0? F of 0 just gives us that 1 back again. So what do we think this function is? If its integral and its derivative end up being the same thing as it, what should n equals 0 to infinity of x to the n over n factorial become? Should be e to the x, right? Its derivative and its integral are itself. This series should represent the function e to the x. And if we go into Desmos and we graph e to the x, right, we know it looks like that. If we go in here and graph the sum from n equals 0 to, we'll just start at 1, x to the n over n factorial, it's going to have some trouble here because n factorial gets very large very, very quickly. But if we go in and change this to like 5, we can see that it starts to line up pretty nicely up against that function, doesn't it? And if we go to 10, well, even better, right? Or if we go to 20, 120 apparently, it starts to go even further, right? Lines up even for an even larger piece of this. It's struggling on 120 there. There we go. But we can see that it's starting to line up really pretty nicely on this. And if I were to keep zooming out, we'd see there'd be a point where it would eventually diverge off of here. I don't know how far out it is. Looks like it's around here. It's starting to diverge off of e to the x, right? You can see that it's sort of going up a little bit there. But Desmos is slow because it's trying to calculate, 120 factorial, which is a pretty big number. It's having trouble with the fine detail there, but it's zigzagging up and down and up and down and up and down and up and down. Just a ton of times, 120 different times, because it's a 120th degree polynomial in between here. But if we were to keep putting in numbers, we would find that this would keep extending out. If I were to be able to go to infinity, x to the n over n factorial would line up perfectly with e to the x. And this is the first series that we will talk about that converges for for all real numbers. And this is a very important series. It's a series that you're going to want to know and memorize because we're going to manipulate it in the future. That's pretty cool. From a nice little simple power series representation. Good or no? Any questions on anything? How did someone discover this? Well, good question. I couldn't tell you exactly how somebody discovered this specific one, but there was these, yeah, I mean, there was a bunch of mathematicians that were dealing with series. The most famous of them were a guy named Taylor and a guy named Maclaurin, and they both have different series named after them, Taylor series and Maclaurin series. And, you know, just working around with manipulating different things to see what happens. Basically, there's no, I don't have an exact answer to that.